That's
Let's
just like this
let's talk about
gross.
that. Let's talk about that and see what we work out on that. And let's see, what am I trying to do? Let me share the screen. That's what I'm missing. Let's go. There we go. That's kind of a mess, isn't it?
There's a question for you.
Okay. All right. Let me see. These problems are all the same thing. So, but they're fun. You'll get your, and look, I know AI will probably answer this pretty quick with like 60 to 75% accuracy maybe, but I think it's fun to kind of go through the details, right, and understand it, because just because AI tells us something. Consider the polynomial x to the 6 minus 3x cubed plus 1, and let f be the splitting field over q. Expect this to work out fairly nicely because the Galois group, if that's an irreducible polynomial, the Galois group of that has to be a subgroup, a transitive subgroup of the S6, and there's something like 16 of those. This will be kind of another ones. Number 8, show the complex conjugation is a non-trivial automorphism of f. And all these problems, I give you a polynomial and f is the splitting field. So in other words, what happens is you take all the roots of this and you adjoin it. We've seen that's actually a normal, and we're always in characteristic 0 here, so it's separable. So these extensions are always Galois. Show the complex conjugation is a non-trivial automorphism of f. That actually shouldn't be too hard. Show that if alpha is a real root, actually I don't have to say real there, but it has some pizzazz to it. If alpha is a real root of this polynomial, show the map induced by alpha goes to alpha inverse gives rise to an automorphism of q adjoint to alpha. Notice this is a subfield of f. I don't claim it's the whole thing. And finally, find the Galois group of f over q. If you ever hear the terminology, find the Galois group of polynomial, what does that mean? That means you're finding the Galois group of the splitting field of that polynomial. Consider the polynomial x6 minus x cubed plus 1. Notice I did change the 3 to a 1. Let f be the splitting field of little f over q. Show there's an intermediate field E such that q is between, or E is between q and f of degree 2 over the base rations. Find the Galois group of f over q, and for each intermediate field E, not necessarily the one up here, in the extension, find an alpha in f such that E equals q alpha. I might regret doing that because, as you might be able to guess from this, there's not a unique answer, right? So I hope people come up with something reasonable, right? Because, for example, any alpha that works, so will alpha plus 87 over 73, you know. And finally, consider the polynomial x to the 6 minus 4, and let f be the splitting field of f over q. Find the Galois group of f over q. Okay. So, actually, I think they'll be kind of fun aside. So, okay, any questions? Okay, so here. Okay, oh yeah, I remember. There's that loose end from last time. So let me just tie together. So what we have from last time is we've constructed an algebraic closure. I think hopefully I convinced you of everything modulo that one detail I left out. So in construction, K bar. an algebraic closure of the field K, is in step one, we constructed this. Uh, right? And we looked at the ideal. Generated by all polynomials in this form, right? Now, the detail I left out is I claim well, if not, so this is as far as we got. Mm, if not, then I can write one as little, and let me tell you what I mean by this notation. These are specifically generators of the ideal, and the G's are just elements of the ring, just anything you want. Now, here's what I would like to do. I want to get 0 equals 1 to get a contradiction, right? So I would like to plug in something to F1, F2. I would like to plug in something for these variables, XF1, XF2, XFK, that gives me 0, right? I'd like to do that. But of course, these FIs are irreducible and there's no guarantee I can do this. But I do know this. There exists a finite extension. Let me call it E over K, such that each Fi X Fi has a root Ri. Everybody agree with that? That's one of our big things, right? So this thing right here may not have a root in K, in fact, it probably doesn't. But on the other hand, in a finite extension, I can just adjoin a root of this and go to the first extension E1. Then I can go over E1 and enjoy a root of this, maybe a possibly bigger E2, and so forth and so on. So everybody okay with that? So in this extension, and of course this is contained in E, or I should say an isomorphic copy is contained in that. R is contained in an isomorphic copy of that. Now, in this larger ring, plug in Ri for XFI and 0 for all other variables appearing. Right? All the variables that appear here, here, and all the G's. Plug that in. That's a homomorphism essentially. And since I get 1 equals 0, which is the desired contradiction. So in other words, if this ideal is proper, if I is proper, then you get an equation of this form. This equation lists to the higher field, but this equation, it can't happen even in the bigger. Yes.
I wanted to ask, like, wasn't the point of making this ring K adjoin XF to like stray away from inducing this extension with all the roots?
There's only finite many.
Hmm.
I mean, if the algebraic closure is a finite extension, it's simple to do, right? The whole point of the algebraic closures is not, is in general, you don't expect it to be finite. So what this, we know we can build this extension because you're only adding a roots of finitely many polynomials, right? In fact, you just need one for each, right?
And right
And that's a
there,
construction we've already done.
right there, one equals all of that entire thing. But like, I is generated by possibly infinitely many polynomials.
Mhm.
So when you expect in general, they need to use it
Never.
all infinitely?
Never,
Never.
you never have an infinite sum. This is, go back to analysis, no infinite sums here, right? Everything's finite. Right, that's the thing. So if you have a polynomial ring, so if you have something like this. Well, let me just do something more familiar. There are infinitely many variables. And in fact, I'll give you an infinite list of things in this ring. X1, X2, X3, X4. These are all elements of the ring. You never see infinitely many of them together. Right? Because everything's a polynomial. All the monomials only consist of finitely many different variables and so forth, right? So it's the same thing for here. Here is, and you put your finger on it. So how would you define this? We all know what this is, power series. I'm not going to worry about it, right? You can think of this. You can pull this apart piece by piece, right?
For the way we define one, is the G, like, are you plugging in a vector?
No,
Or
I
is
just
that
put,
just
I just put those X vectors to signify that they could involve very many variables.
And
right?
then why is the identity, or like, why is one not just like the one, like polynomial with constant one? Why is it like a?
No, it is, that's what it is.
Oh,
But if this ideal is not proper, then there should be a linear combination of all of these things to get you the polynomial one. Let me ask you this. What's that? This is problematic because this thing right here, you can think of this as the unit. You can think of this as the union you can think of this. However, does anybody see what the potential problem with this is? So look at this element here. I'll call this potential powers. You see what the pattern here is? This is a single power series as X goes, and you've got this kicker every time, right? This is not in the union of Rx1 up to Xn forever, right? Because this single power series right here is not in any finite number of variables power series, because this power series by itself uses infinitely many variables. Agree? this is part of the problem thinking about the infinite as well. When somebody says this, I'm like, what are you talking about? Because there are at least 3 different definitions of what this means in literature, and they're all different, right? So it depends on how you define it. The polynomials, not a problem, because the polynomials being finite sums, there's a little bit of control there, so. Okay. Other questions? Okay, let me give you a kind of a last corollary in this. Well, if K is a field and S is a set of polynomials over K, then there exists a splitting field for S over K. And I will also point out that the splitting field, a splitting field for a set of polynomials is always Galois. The set of polynomials is separable. So if you have a splitting field over a characteristic 0 field, it's always going to be a Galois extension, as a matter of fact. So we've used separability a little bit. We've talked about it a little bit in the homework. Let me, I'm going to talk a little bit about separability. I'm going to go through this a little bit quickly, just to kind of cover maybe some bases. And I'm gonna pretty much do this in the context of algebraic, because separability does depend on polynomials. Separability. So let's let K be a field and F an area for polynomial. And F of X and K of X, here it is. Then F is separable if it splits, or if it factors into linears. Sure. Yeah. Linear. In some splitting field of F. For F of K. Okay, here's a couple other terminology. We say the element U is separable. U some field extension of F. I'm sorry, K. And U is algebraic over K. We say U is separable if it's minimal polynomial. Okay, so take some element field extension that's algebraic, it's got a minimal polynomial. If that minimal polynomial is separable, we say the element is separable. We say F separable over K. If U is separable over K. For all Q and F. Here is something that you did in your homework probably or doing. Lemma 1442. What can it be? Fields. And U F algebraic over K with minimal polynomial at X. Then U is separable over K. If and only if GCD f of X at prime of X is 1. Okay. From homework, we have, I believe this is the homework problem. F of X is separable if and only if GCD f of X is 1. Let me give you kind of this little side result. I love this. Suppose the is Actually, let's just try this. Yes. And to be clear, I mean identical to the zero polynomial. Any ideas how to do this?
So you'd probably want to start by giving like a general form for f of x, and then take the derivative and have some sort of argument for.
Well, so from what we've done in the homework before, right? This condition. Meaning f of x has a multiple root. We'll call it omega. Right? That's from your homework, etc. Right? And in fact, you probably proved in your homework that this multiple root is also a root of the derivative, right? So, and f has a multiple root omega, and f prime omega is also. Anybody see what the problem is? I mean, at this point, it might already kind of be rearing its head. But if f of x is irreducible, isn't it the minimal polynomial? That's crucial here. It is minimal polynomial. Or omega. But this is, but f prime I know one of two things has to happen about omega. It means, in general, degree of f prime is less than degree of f, or what's the alternative?
Same.
Well, you're not going to get that figure forever.
Just like about zero.
No,
Not
one of them is
irreducible,
zero.
okay.
The degree either falls by one, or certainly if the degree of this is x to the n, there's going to be no nth degree term here. But the only other thing it could do is it could crack all the way down to zero, which is undefined degree, right? So there's an interesting consequence to this. And this will come up in our discussion here. So here's an interesting consequence. So if I have an irreducible polynomial, and the GC, if it's irreducible, the GCD of it and its first derivative is not one, then either the polynomial, well, that's an outright contradiction. right? Because, if f of x is zero, that's the, minimum polynomial for this. Unless the derivative falls all the way to zero. Now, if this is an irreducible polynomial, then it has to have degree at least one, right? All constant polynomials are units, well, other than zero. So that means corollary. If K and F are characteristic zero, then F is separable. Okay. Any characteristic zero is separable. I've said that many times. Here's the proof. If not, there exists omega, algebraic omega F, algebraic over K, with minimal polynomial f of x and k of x, such that GCD f prime is not equal to 1. Which implies f prime of x is identically 0 from previous. Agree? But then, therefore, f of x is constant. Because in characteristic 0, the derivative of any polynomial just drops the degree by 1, right? So if you've got the derivative to be 0, then it can't come from any higher degree polynomial. It has to come from a degree 0. It has to come from a constant, right? Which implies f of x is 0, which is a contradiction. Because why does it have to be 0? Well, I know it's going to be constant. And if it's got a root, the only constant polynomial that has a root is the 0 polynomial, but that contradicts the irreducibility of f, right? So characteristic 0 can't happen. Everything's separate, right? Here's another observation. Here's another corollary. This observation. Let's suppose I'm gonna write this out. So we sorted out the characteristic 0 case. Well, what if we have characteristic p? Suppose you have an element that's not set, right? So this will kind of give us a way to look at things. Let f of x equal, let's make this easier on ourselves, xn plus kn minus 1, xn minus 1, k1x plus k0 be minimal polynomial over omega. Well, since then right? Because it's got a separable element, so the GCD with its first derivative is not one, so we know it's derivative zero. So f of x, what can we say about f of x? This tells me something. How can you take this in characteristic p and get zero, identically zero for the?
Is the degree.
Right, even more than that, it has to be a polynomial in XP. So f of x is a form. I can modify this a little bit. X to the p n plus k n minus one, x p n minus one, k one x p plus k zero. So it has to be a polynomial in the variable xp. And so if you have a polynomial that isn't where you just where the taking the derivative, this doesn't immediately give you zero, you know that this polynomial has roots that's not separate, right?
I just,
Or that is. Yes.
for that lemma, like, why can't the degree be less than f? Like, if we, like, why can't the degree of the derivative be less than f? Like, why does it have to be zero? Because then would that make it?
Well, what I'm saying is either this happens, when you take the derivative, it drops the degree, or the derivative must be zero.
Oh, so
See, the zero polynomial has an undefined degree, so that's why that's separate cases required.
okay, but what happens in the case that it just drops the degree?
Oh, well, so this is part of the proof here, so, this is what we're proving.
Mhm.
If this happens here, if the GCD is not one, then the derivative is zero. What I'm saying here is we have the GCD is not one. This means that this has multiple root omega. And this omega, the root is actually shared with the derivative, right? Here's the problem. F of x is the minimal polynomial. So there is no polynomial of degree smaller than that has omega as a root.
How do we know that f prime is in the same? Like, cause what if like when
Oh,
you
it's in the same, okay, because those exponents that you bring down when you do the rule, they're just like integers. And that you can consider that
okay.
in any field.
Okay.
Right. Yes.
The right forward, what is the corollary exactly, that the minimal polynomial will be of the form at the very bottom?
Yes.
Okay.
So is f prime zero the assumption there, or is that something you get from the?
This is just me talking about what we've done before to explain what I'm writing. Yes, this is what I get for making a corollary on the fly, but yeah, it's just kind of repeating this here. Then f prime is zero, and so f of x must be of this form. Okay, other questions?
The contradiction on the middle board is that omega has a minimal polynomial that f of x equals zero is not a choice.
Right, so you have, now we're in characteristic zero, right? And my claim is, so if not, you can find an element that's not separable. So it must share a root with its first derivative. So you've got this going on, right? By the statement up here, that means that f prime of x is the zero polynomial. But in characteristic zero, the only way that a derivative can be zero is for it to be a constant, right? And that's the difference. Characteristic p, you could have a polynomial like x to the p plus one, its derivative is zero. But you can't do that monkey business in characteristic zero because your exponents are never essentially zero.
Where do you have that happens that f of x equals zero? F of x being constant.
Right, so f of x is constant, but it was a polynomial of which omega is a root. The only constant polynomial that anything's a root for is a zero polynomial, and that contradicts the irreducibility. Okay. Right. All right, so here's another kind of, let me kind of upfold here on this. It turns out that you can kind of, in a certain sense, kind of segregate separability and inseparability in sort of an organized fashion. You can kind of, you can kind of file them away in different, in an organized way in the following sense. Let me first give you this definition. Definition. Let's let K and F be an extension. An element, U and F, which will implicitly be algebraic, is going to be termed purely inseparable. Purely inseparable over K if its minimum polynomial is of form x minus u to some power. F is purely inseparable over K as an extension. If all elements of F are purely inseparable. Okay. So let me give you an example. Let me point out, by the way, I bet y'all can figure out. I mean, suppose that we have K. Let's just consider these to be sets so far, but it turns out that so suppose that I look at K and I've got some field extension to F. And I don't claim that you put these two things together, you get all of that, but I can certainly consider the subset of elements of F that are purely inseparable over K. And I can consider the subsets of F S that are separable over K. And I'm assuming F is algebraic. What's that? The elements that are both purely inseparable and separable.
All the elements, okay.
Take an element K, its minimal polynomial is x minus K. So it's separable and technically purely inseparable with n equals 1. On the other hand, if you've got something that's both purely inseparable and separable, its minimal polynomial has to be this because it's purely inseparable. But if it's separable, m has to be 1, which forces the element to be in K. All right. So I think that's a good observation to make. Here's an example. Let's let F equal C2 rational functions. call this one K. This is the baby. In this example, it turns out that F is, in fact, F is a purely inseparable extension here. Because, for example, notice that so I'll just do this for a polynomial. Let's say let's go out. I'll do something general like this. Well, this is well, actually, what am I gonna?
Is this the minimal polynomial with stuff?
Let's call this U. The minimal polynomial of this is, well, do you know what it is? I guess since this is over Z2, I could erase that A and BM, but whatever. It's well, plus or minus doesn't matter, it's characteristic too. Command over. Notice that this thing is a rational function over Z2 and the variable x squared, right? And notice that when you plug this in, it works because you square that, everything's characteristic too. So, and notice that this is so this element here, which is an arbitrary element of this, not in here, is purely inseparable. Right? So this is a good example of a purely inseparable extension. Okay. Any questions? I think that's a good place for today. Any questions? All right, we'll hit this again next time.